analysis of a voltage divided by a circuit. Before calculating the Q point, that is to find the ICQ and VCQ values, we need to check if the Rin base is greater than 10 times of R2 first. That is, we start from the input base circuit that is used to determine VB and check the transistor loading condition. In this case, Rin base is calculated to be 55K while 10R2 is 47K. The loading condition is met and hence the input base impedance has minimum effect on the base voltage VB and can thus be ignored. After checking that the Rin base is greater than 10 times of R2, we proceed to determine the voltage value of VB, the base voltage of the transistor in step 2. Using voltage divider rule over R1 and R2, we find that VB is actually equal to the voltage across resistor R2. Hence, VB is equal to R2 over the sum of R1 and R2 multiplied with the voltage supply VCC. Substituting the values of R1, R2 and VCC, we get 2.07 volts for VB. After determining VB, we then proceed to determine the value of VE, the emitter voltage of the transistor in step 3. Observe that to determine VE, VE is the difference between VB and VBE. VBE is the voltage difference between point B and point E, which is VB minus VE. Rearranging this equation in terms of VE will then give VE equal to VB minus VBE to give a value of 1.37 volts. Step 4 is to determine the emitter current IE. IE can be derived using Ohm's law by dividing the emitter voltage VE with the resistance of RE to give a value of 1.25 milliamperes. Moving on to step 5, we determine the value of the collector current IC. IC is equals to IE since the base current IB is assumed to be negligible. Hence, IC is equals to 1.25 milliamperes. Determine the value of IC, which is actually the ICQ value of the circuit. We proceed to determine the value of VCQ in the next step. To determine VCQ, we use Kirchhoff's voltage law or KVL at the output collector emitter loop. To derive the KVL equation at the output collector emitter loop, we observe that the voltage supply VCC supplies voltage to 3 parts, namely voltage across the collector resistor RC, voltage across the collector and emitter terminals VCE, and lastly to the emitter resistor RE. Hence, VCC is equal to the sum of these 3 voltages along the collector emitter loop. The voltage across the collector resistor is derived by multiplying collector current IC with the collector resistance RC. The voltage across the collector emitter terminals is VCE. And the voltage across the emitter resistor is derived by multiplying emitter current IE with the emitter resistance RE. Since the emitter current is the same as the collector current, we replace it with IC. We can then simplify the equation as such. To find VCE, we rearrange the equation in terms of it like this. To find VCE at the Q point, we substitute IC with the ICQ value which we had earlier derived and determined in the previous step. Substituting the values of VCC, ICQ, RC and RE, we obtain the value of 4.87 volts for VCQ. Thus, we can conclude that the Q point coordinates are 1.25 milliamperes for ICQ and 4.87 volts for VC. We need to first derive the DC load line equation from the output collector to emitter loop. To draw the DC load line, we need to first derive the DC load line equation from the output collector to emitter loop circuit, which is actually equation 1 from the previous page. Substituting the values into the equation, we obtain the following. To find IC set, which lies on the y-axis, we set VCE equal to 0 into equation 1, since there is no VCE value on the y-axis. Therefore, IC set will be equal to 2.44 milliamps. To find VC off, which lies on the x-axis, we set IC equal to 0 into equation 1, since there is no IC value on the x-axis. Therefore, VC off will be equal to 10 volts, the value of the VCC supply voltage. Now let's try to draw the DC load line and locate where the Q point lies along the DC load line. Before we do so, we need to indicate where the IC set and VC off points are. The 2.44 mA current lies on the y-axis and is the IC saturation current. The 10 volts voltage lies on the x-axis and is the VC off voltage. Once we get to know the IC set and VC off points on both axes, we draw a straight line to connect the IC set and VC off points. This straight line is the DC load line. The Q point lies on this DC load line and it consists of y and x coordinate values. The y coordinate value of the Q point is ICQ and lies on the y-axis between 0 and IC set. We project this point horizontally to the DC load line. The x coordinate value of the Q point is VCQ and lies on the x-axis between 0 and VC off. We project this point vertically to the DC load line. Hence, the Q point is finally indicated on the DC load line.